All right, thanks. You all hear me? Not too loud, not too quiet, just right? Cool. Hi, everybody. My name's Brian. I do music and machine learning and stuff like that. So I'm going to talk mostly about the nuts and bolts of the library that I developed to make the rest of my research possible. And I'm not going to talk so much about the actual research, but if you're curious about it, I'm happy to talk later. So just a little bit of context. I come from a field sort of called music information retrieval, which I'm pretty sure most of you have not heard of. We have a society, apparently. It's right here. It's called ismir.net. And basically, it's a loose conglomeration of people that are interested in analyzing and summarizing and indexing musical content. And that can be anything from audio to score to listening histories to historical documents, anything that's kind of related to music. I mostly work on audio content analysis. So from my perspective, the interesting problems are things like summarizing features of audio that are musically relevant. So things like note onset events, beat tracking, structural analysis, high-level things like predicting tags, like is this a rock song, is it a hip-hop song, automatic transcription, recommendations, search, cover song ID, all that kind of stuff. So that's roughly what I do, but I'm just one person in this kind of strange field. So the community involves a lot of people coming from different backgrounds, much like this one, but different. So in particular, it involves a lot of DSP. So if you're happy with signal processing, good. Machine learning and stats, but then also more the humanities end of things. There's musicology, library sciences, and cognitive science all are pretty well represented. So that's roughly kind of where this is all coming from. So my typical pipeline looks something like get a bunch of audio signals, extract a bunch of features from them, build a statistical model, and then start to think about some questions you might want to answer with that model. This part of the talk, this talk entirely is only going to cover that first bullet point, and maybe a little bit of the second one, but not too much. So that's kind of motivating what Librosa is for. Python module to analyze audio signals in general, but geared towards music. What it includes are basically the nuts and bolts that you need to build an MIR system, and reference implementations for some more commonly used methods and helpers and shortcuts and commonly used things. So that's kind of what it does. Why did I sink all this effort into it? About 3 years ago now, just shy of 3 years, we have our annual conference in the fall. And we had like a late-breaking lightning talk session on adopting Python in MIR. As you might imagine, Python might not be the most natural choice for a lot of people, especially the DSP people who make most of the tools that we use. They really like MATLAB, and I'm sure you all are familiar with that kind of person. I used to be one. It got better. So there was a lot of interest in moving to Python for a lot of reasons that I'm sure you're all familiar with, things like API integration, dealing with text, better reproducible methods. The list goes on and on. A lot of interest, not much movement. And basically what we identified in this like half-hour session that we had is that we lacked the infrastructure to make it work. We didn't have all the legacy infrastructure tools, piles of MATLAB scripts, et cetera, that people had grown accustomed to using. So I just finished my PhD, and I was looking for new stuff to do, and I thought, that's a problem that I can help with. I can build infrastructure. I like doing that kind of thing. So that's what I did. So just a quick word about what the design goals of this library are. So number one, it has to be easy to use for MIR people. Particularly, it has to be easy to port over from MATLAB code, so that means we're not going to have a lot of objects involved. There's not going to be a lot of tightly coupled APIs. It's going to be pretty flexible, pretty open, and very easy to shoot yourself in the foot, but that's kind of intentional. We want things to be consistent, so a lot of the code that we're integrating is coming from different sources, right? You have your STFT implementation, he has his, and they both generate roughly the same thing, but they might be a little bit different. We want to be able to support backwards compatibility with everyone, and we want to do it consistently with the same interfaces, same conventions, same variable names, et cetera, et cetera. We do backwards compatibility testing mostly through very exhaustive regression testing. It's all automated. Things are modular in the sense that if you don't like my particular, say, onset strength detection function, you can plug in your own, stick it into the beat tracker, and off you go. Things still work together nicely. And finally, we focus pretty heavily on quality control, so there's a lot of testing, a lot of documentation, and real focus on making the code readable. So it's all pure Python. You should be able to crack open any function and see how it works and get a pretty quick idea of what it does. And that mostly comes out of my own frustrations in porting MATLAB code. And I'm sure you're all familiar with that problem too. So the rest of this talk is basically just going to be demo time because I don't think it would be that interesting or relevant to go into the details of how all this stuff works. If you want a thorough overview, we have a paper that's in the proceedings, which should be somewhere. Or you can check the API documentation if you really have some time to kill. Or you can just pip install it and hope for the best. Pip install will work. Some of the dependencies are a little bit trickier to make everything fit together, but we're working on that. And it works on 2.7 and 3.4, so we're all pretty happy. Okay, so blah, blah, blah. What does this actually do? So first thing you might want to do is load in some audio. Seems sensible. Here's some just boilerplate code to make this work, and then helps to actually import Librosa. This is all just stuff to make things interact well. First function that we're going to look at is load, and it gives you back an audio time series as an numpy array and the sampling rate of the audio. By default, everything is going to be downmixed to mono and resampled to 22 kilohertz. You can override that easily. So we get Y and SR, so time series sampling rate, numpy array, integer, and that's kind of what it looks like. So the song's about a minute long. You can do the math if you want. So okay, loading, that works. And this will handle pretty much any kind of compression codec you want. This is using audio read on the back end, which then multiplexes to like every other codec, if it works. Sometimes it doesn't. You can play things back. We have a demo track that ships with it. It's a nice Creative Commons 0 thing that I found in the Free Music Archive, so hopefully this will work. Is that too loud? No. Okay. I'm going to be using this example a lot for the rest of the talk, so you should have a rough idea of what's in there. Okay. So that's it. Basically just goes on and on like that. If you're into plotting waveforms, we can do that pretty easily. When you plot waveforms, you don't usually want to plot the time series natively. You want to downsample it and do some shaping. So we have a display module that does this kind of thing for you. You can see the very, very bottom. It does time axis formatting and all that kind of stuff. So that's kind of fun. I don't particularly like looking at waveforms, but it's a thing you can do. More interesting are spectrograms. So this would be like how the audio spectrum varies as a function of time. We store these in general as 2D numpy arrays. First axis is frequency, second axis is time. And just a little bit of terminology if you're not familiar with this kind of thing. So I'm going to use SR to denote the sampling rate. It's how many times we sample the signal per second. A frame is going to be a short snippet of a signal. NFFT is the number of samples that are in a frame. And the hop length is how far you move the frame between each column of your spectrogram, basically. We have some defaults. These are persistent across all functions, but they're easily overridden. But if you just want a spectrogram, you can do that. You say librosa.stft. That computes the short time Fourier transform. We also have inverse STFT. We also have instantaneous frequency STFT, and so on and so forth. This is just a picture of what that's doing. Yikes. All right. So yeah, it's pretty modular. You can plug in your own window functions. You can do all sorts of things. I'm not going to dwell on this too much. More fun stuff you can do, plot spectrograms. So this is showing time and frequency, just like I described. This is with the SpecShow function, which is kind of a smart wrapper on top of matplotlib's imshow. It does a whole lot of stuff that I'm not going to get into. but there are a few things that you should know about. So the first thing is this is a linear frequency map, which is usually not what you want. The reason for that is all the action that you care about is typically in the bottom of the spectrum, for music at least. So instead we can plot this on a logarithmic frequency axis. So now if you look at these labels, now this is log space instead of linear, and you can kind of see more structure. So that's fun. I think Alan said earlier that the Fourier transform is the coolest thing ever, and I would amend that to say that it's really cool, but the constant Q transform is also really cool, possibly even cooler. So that's directly doing a logarithmically spaced frequency representation. So we do that with the CQT function. And my mouse stops working. That's no good. There we go. So that looks like this. And this is nice because one vertical move is one semitone, right? So things are kind of shift invariant vertically as well as horizontally in time. You do logarithmic amplitude scaling. Makes it a little bit easier to see what's going on. This is also very, very flexible and has tons of parameters that you can play with. Okay, going to zip through some of this stuff. There's more to it than just Fourier features. You can do all sorts of different spectral features. An interesting one is chroma. So that's how much energy is in each pitch class, not each pitch. So right, there's C1, C2, C3, C4. I'm going to collapse those all down to C, and that gives us what we call chroma. That's easy to compute. You just call feature.chroma. And that looks kind of like this. So you can see the white keys on the piano up here. The song has a lot of E in it, and then there's this little kind of chord progression that repeats a whole bunch. You do all sorts of other spectral features, Mel spectrograms, MFCCs, Tonitz features, spectral contrast, bandwidth, all that kind of stuff is in there. Those are fun to play with, but I'm not going to talk about them. We have an audio effects module, which maybe I'll skip the examples. But this can be useful if you want to separate components. So typically when you want to do a harmonic representation, you want to throw out transients, right? Because a drum hit isn't going to be all that harmonically relevant. So there's a nice implementation of harmonic percussive source separation. I'll just play the percussive component, and you can get a feel for what this does. So that's the percussives, this is the harmonic. Right, so we get the harmony, but not so much the percussion and the transients, and gives us a little bit cleaner representation. Right, so here we have the original CQT. This is the harmonic component, which has all the horizontals, which is what you want, stable tones. And the percussives here are vertical stripes. Depending on what you want to analyze, one or the other might be more useful to you. You do fun things like onset detection and beat tracking. Those are pretty easy to do. Get the onset strength and detect events. And here I'm just plotting the onset strength function in blue and all the detected events in red. So each one of these red lines we think is a new note. Don't worry about the plot code garbage. This is just to make it look nice-ish. You can track beats and estimate tempo. That's also pretty easy to do. So here you can see that the detected beat events are much more evenly spaced than the note onsets because beats are kind of a subset of notes. They're evenly spaced and they're pretty much correct. If you want to listen to what that sounds like, you can convert beat frame indices back into times and sonify them. And we'll put a little click track on it. It sounds like this. So it gives you kind of a metronome. It's dynamic. It'll adapt to slight tempo variations and kind of do the right thing. Okay, very last bit is just how do we deal with time, repetition, and structure? And this will be very, very quick. Yeah, very, very quick. So we can synchronize features in between beats. Gives us some dimensionality reduction. You can do some history embedding to get context for features, so it's not just a single frame, but the frames around it. And you can use that to build a recurrence plot and encode structure. So this would tell you, if you have a real sharp eye, that maybe the song is in 6/8 or possibly 3/4. if you look at the spacing between the repetition events. And this is the kind of thing that I like to work on in my research, is analyzing this type of picture and figuring out what information is in there. So there's a lot more stuff to parse these things and filter them and do fun stuff with it. So I think that's where I'll stop. So I've just shown you a few of the building blocks that are in there, but there's a lot more. We just released 0.4 like 2 or 3 weeks ago, but we're still developing pretty actively. There's some related projects for doing other things that I can't spell correctly. We have pretty thorough documentation, code online, and lots of really awesome contributors who I would not have been able to do this without, so thanks to them, and thanks to you, and I'll take any questions.
Thank you. Over there.
At the beginning, I thought I heard you say that this was all in Python, but I'm having a hard time believing your FFT is like in Python, so I'm getting the performance that I just saw. So what did I do wrong?
So it is all in Python. The STFT implementation is fairly well optimized, and it's doing partial blocking. So it's not doing a single frame at a time, and it's not doing the whole signal. It's doing chunks, and that chunk size has been optimized. But yeah, it actually is Python. I'm not hiding anything. I did try to make it Pythonized yesterday, and it didn't get any faster. So that's kind of interesting. I probably don't know what I'm doing.
Over there.
I have a project that does transcription into not score, but NES chiptunes. So it'll take an audio file and convert it into 2 square waves, a triangle wave, and a noise channel. And depending on what you put into it, it works kind of okay. But for the most part, no, I can't. That's a very active research topic. Okay, so the question was, can we do things like vocal activity detection, beat tracking, alignment, stuff like that? We can give you the features to do it. I don't want to start putting supervised models, like things that are really statistically dependent on particular data sets, into the library. I want to keep those separate. But it can give you the features to do it.
Thank you. We have to cut it here. Let's thank the speaker again.